Understanding physics. This is something that a lot of students find very, very tricky at first, because it is tricky. Once you get your head round it, it should be pretty straightforward. Gravitational potential. Okay, so now some things are the property of an object, and some things are the property of a point in space. Now, what do I mean? Well, see this car, it has mass, it might have charge, momentum, kinetic energy, gravitational potential energy. Now, these are properties of an object. Some things are the property of a point in space, whether there's an object there or not. And the two that are really important now, field strength and potential. So the field strength at that point, the potential at that point, okay, whether there's an object there or not. So gravitational potential energy is the property of an object. Potential is the property of a point in space. Now, what is potential? Well, it tells us how much potential energy, unit mass or unit charge, if we're talking electric fields, so unit mass or unit charge, in other words, a kilogram or a coulomb, would have if it were at that point. So if there was a kilogram at that point, how much potential energy would it have? But the important thing I want to get across on this slide, potential is the property of a point, potential energy is the property of an object. And gravitational potential has the symbol capital V. Remember, it's joules per kilogram. Yes, if you remember that, I think you're halfway there. V is joules per kilogram. In an electric field, it's joules per coulomb, but here, joules per kilogram. That's for a kilogram. If you had a mass m, then to get the gravitational potential energy, it's just mv. Just multiply by m, because that's how many kilograms you've got. Let's leave potential alone. We'll come back to it in a minute. Let's look at some basic stuff. First of all, a uniform field. What do we mean by a uniform field? Well, if I'm lifting a mass m, a height h, in a uniform field, well, a uniform field, little g has the same value everywhere. In the room that you're in at the moment, it's 9.8 newtons per kilogram. And that's near the floor, near the ceiling, near all of the walls, it's 9.8 because you are in a uniform field. If we represent a uniform field with field lines, then my lines are straight and parallel and evenly spaced. Okay, and that is a uniform field. Now, energy transferred, which is like, could be work done. If you were lifting up the mass, work done. It's gain in GPE. If you let go of it, then the work done by gravity or the gain in kinetic energy, the energy transferred is force times distance, which is mg times h. Okay, so it should be a very familiar equation. Gain in GPE is mgh from GCSE. Now look at this. This is not a uniform field. This is a non-uniform field. Looking at my field lines, I can tell, looking at the field lines, that the field gets weaker because the field lines are getting further apart. Okay, in a non-uniform field, little g is getting weaker. In fact, little g follows an inverse square law. Yes, g is proportional to 1 over r squared. That's an inverse square law. If r gets twice as big, then g is a quarter. If r gets 3 times bigger, then g is a ninth. Yes, it gets weaker as we move away from the Earth. Look at this graph. On the left, at the surface of the Earth, g is about 10. At a distance from the Earth equal to the Earth's radius, it's 2.5. Why? Because it's a quarter. Yeah, look at the graph now. If r is the radius of the Earth, at r it's 10. At 2r it's about 2.5. At 3R, it's about 1.1. It follows an inverse square law. Now, the question is, energy transferred. Can we use MGH? How much work do we have to do to get from A to B? Can we use MGH? And we cannot use MGH. Why not? Because what value of G do we use? Going from the 10 to the 2.5, do I use 10? Do I use 2.5? Do I use an average? And I can't use an average because the graph isn't a straight line. So how do we work out the energy transferred between 2 points in a non-uniform field? And we can't use MGH. So this is where potential comes in handy. How much GPE would a kilogram have at A? Well, that's the potential at A. How much GPE would a kilogram have at B? That's the potential at B. And if you know these, you can work out the difference in potential between A and B. And then if you multiply that by the mass of the object, that's the energy transferred. So the energy transferred is M times delta V. If you know the potential at A, if you know the potential at B, you know the difference in potential, you know the difference in potential energy of a mass. So gravitational potential, V. Again, I'm repeating myself, it's how much gravitational potential energy a mass of 1 kilogram would have at that point. That's not the formal definition, but it will do us for this video. This is how we work it out. It's minus gm over r. V is minus gm over r. Note, again, it's the property of a point, not an object. Note that it is negative. I'll talk a lot about that in a minute. It is a negative quantity. Notice the difference between that equation and G is gm over r squared. Okay, so little g, that equation's positive, this one's negative. Little g is over r squared, this is just over r. It's an inverse law, not inverse square. So the energy transferred when a mass moves between 2 points in a gravitational field is m times delta v. Yes, m is the mass of the object and delta v is the difference in potential between those 2 points. If you understand this, you can do this question here, no problem. So pause the video, pen, paper, calculator, get it done. I'll show you the answer in 3, 2, 1. There you go. So calculate the potential where this meteor is. Notice that it's minus 1.93. Calculate the potential at the surface of the Earth. Notice it's minus 62.5 times 10 to the 6 joules per kilogram. And then the energy transferred. In this case, it's the gain in kinetic energy, or the work done by gravity. Same thing, m delta v, and it's the difference between them. Okay. One little trick, by the way, in this equation, you know, it's a minus, minus, a minus. What I do is I don't worry about the minuses. I just say it's the big one minus the little one. If we're working out kinetic energy, the answer has to be positive. You can't have negative kinetic energy. So it's just the big number minus the little number in this case. Look at this diagram. Now, the blue lines are equipotential surfaces. Okay, surfaces because it's three-dimensional. So each one is actually a sphere. Yes, so each of these blue lines represents a sphere and it's an equipotential, and that basically means that, well, because the value of r is the same, then the potential will be the same at any point on one of these surfaces. Looking at the diagram, notice that the equipotentials get further apart. Can you explain why they get further apart? And the reason they get further apart is, as we move away from the Earth, the field gets weaker. So for the same amount of work against gravity, you'd cover a bigger distance. Because gravity is getting weaker, for the same amount of work against gravity, the distance that you travel would be bigger. Yes, so basically my potential well, the sides of the well are curved. This is a little bit like contour lines on a map. If you look at a map and you saw rings like that, that would either be a hill, like a volcano, or a well. In the case of gravity, it's a well. And we're going to talk about why in a minute. Yeah. So why is potential a negative quantity? How much potential energy would a mass of a kilogram have at the surface of the Earth? We actually worked that out a minute ago. Where would it have zero potential energy? Well, I've got some shocking news for you. We are trapped in a well. Yes, we are trapped in a potential well. We are at the bottom of a well. And I'm not saying we can't get out, but it would take a ridiculous amount of energy to get out. Lots and lots of energy to get out. About 62 million joules per kilogram to get out of this well. We are trapped in a potential well. To escape from the Earth, or just to move away from the Earth, we have to do work, and we have to do lots of work. Okay? If we did enough work, then we could escape from the Earth's gravitational field. We could get to a place that we call infinity. And infinity is very, 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 very far away from the Earth. It's where the field strength due to the Earth is zero. Yes, it's where the Earth's gravitational field is zero. And you'd have to get very, very far away from the Earth, or at least negligible. In real life, negligible, theoretically, an infinite distance away. And basically, we're in this potential well. We're trapped in a well. We would have to do lots and lots and lots of work to escape from the well to get to a place where we would have zero potential energy. Yeah, to get to the outside of the well. And that's so where would it have zero potential energy? Would be at infinity, very, very far away from the Earth. And how much potential energy would a mass of a kilogram have at the surface of the Earth? Well, it would have minus 62.5 megajoules of potential energy. We worked it out in the last question. This is a very, very good video, this idea of potential wells. There's a few of these. I think this is probably the best one. And this guy with a big rubber sheet, and he puts a big massive in the middle, and that represents our gravitational well. And he demonstrates satellite motion and all sorts. I used to do this. One of my technicians made me a fantastic rubber sheet like this, which I used with classes. So if you've understood all that, you can do these questions. Don't be lazy, do them. Pause the video, pen, paper, calculator, and the answers are in 3, 2, 1. Okay, so the velocity at that radius. Now, you should know that at any radius, satellite orbit radius, there can only be one velocity, yes? And I've just derived it there. So F equals ma, gmm over r squared is mv squared over r, little v is gm over r. At that particular radius, it's 3,668 meters per second. Okay, nothing special about that radius, by the way. Kinetic energy is just a half mv squared. The potential at that radius is minus 13.5 times 10 to the 6 joules. Oh, he's done it again, you know. Joules per kilogram. Idiot. Sorry about that. Okay, so the potential energy of the satellite is minus 9.42 times 10 to the 9 joules, and then the total energy is minus 4.71 times 10 to the 9. Why is the total energy negative? What is the significance of that? Because the satellite can't escape. It doesn't have enough kinetic energy to escape the field. It has enough kinetic energy to go round and round the Earth, but if it had more kinetic energy, yes, then it could possibly escape. Yeah, but at the moment, its kinetic energy is less than its gravitational potential energy, so its total energy is still negative. It can't escape. Which leads us on to this next thing. Imagine you threw a ball vertically upwards. How fast would it need to be traveling, ignoring air resistance, for it to be able to escape the Earth's field? In other words, what is the escape velocity of the Earth? And you should be able to do this. So kinetic energy going to GPE, so a half mv squared goes to m delta v. Delta v here, now the potential at infinity is 0, so that term is just equal to the potential at the surface of the Earth. And don't worry about the negative, okay? And so rearranging that equation, we get V is root 2gm over r. Yes? You bung in the numbers and show that the Earth's escape velocity is about 11 kilometers per second. Again, ignoring air resistance. If it was traveling that fast, air resistance would not be negligible. Okay, but ignoring air resistance, that's the Earth's escape velocity. Okay, last tricky bit. This now, V is minus gm over r. You do A-level maths. Could you differentiate that for me? Find dVdr. What is dVdr equal to? And if you work it out, oh, look at that. It's gm over r squared. So dVdr is equal to little g. Now, so what? Well, if we had a graph of potential against distance, then dVdr is the slope. It's the steepness of the graph. It's the potential gradient. Yes, the slope of this graph, and notice that the slope is getting less and less and less as we move away. If you actually got to infinity, then the slope would be 0. And that's because the slope is dVdr. Yes, it's the rate of change of potential, the field strength. The field strength is getting weaker and weaker as we move away from the Earth. So remember, G is dVdr. So G is gm over r squared. Again, you do A-level maths. Could you integrate that for me? And what do you get? We get that the integral of G with respect to r is minus gm over r. Blimey, it's V. So V is the integral of g dr. So what? Well, look at this graph. This is a graph of field strength against r, and the integral is the area under the graph. So the area under the g graph between a certain value of r and infinity is equal to the potential. Yes, it's the work you would have to do to get a kilogram from that point to infinity. I'll mention now actually the actual formal definition of potential is the work you would have to do to get a kilogram from infinity to a particular value of r. And that's why it's negative, because you wouldn't have to do any work. Yes? Anyway, so forget that, it's not important. The graph of G against R, the area is the potential. If it was the potential difference between 2 points, then it would be the area between 2 values of R. One way of thinking about it is if you had a graph of force against distance, and if it was a rectangle, then work is force times distance. So it's the area under the graph. Okay, well, G is just the force per kilogram. So the area is the work per kilogram, and it's not a straight line. So it's not a rectangle, it's lots and lots and lots of rectangles added up. The sum of lots of rectangles added up. In other words, the integral, the area. Finally, to finish this off, if you can answer this question, then I think we're halfway there. How much gravitational potential energy does a mass of 1 kilogram have at the surface of the Earth? And you should be able to tell me by now, if you watch the video, it's not 0, it is minus 62.5 megajoules.